Welcome, everyone. Konnichiwa. Very good. So I did it right. Welcome to my talk. My name is Chris Thalinger, as you can see at the bottom here. I work for Twitter, obviously. I'm wearing the Twitter shirt, so I work for Twitter. And I live in Hawaii, by the way, so I'm wearing my aloha hat. Who's been in Hawaii? Japanese people love Hawaii. I see a lot of Japanese in Hawaii. So first and most important question, and I hope that a lot of hands will go up because I know Japan. Who in this room has a Twitter account? Yeah, that's pretty good. There was a big hole back there. So I encourage you to tweet about this talk. And the people who don't have an account, create one right now, and then tweet about this talk. Twitter has a small VM team, and it's kind of 4 people working on the VM. We have 3 GC engineers, and they are basically 24/7 busy handling all the GC problems that we have with our microservices. And then there's a compiler engineer, and this is me. And I have the fun job. I travel around and tell people about the cool stuff we do, while everyone else is actually working. So if you're tweeting about this talk, OK, I'm talking too fast. I have to talk slower. If you're going to tweet about this talk, please use this hashtag, the Twitter VM team hashtag, so that all the people, my colleagues, know that I was actually here. So why am I doing this talk and all the talks I'm doing? I'm talking a lot about Graal. And before I start, some of you might have seen the Graal VM announcement not too long ago, like 2 or 3 weeks ago. I'm not talking about Graal VM. So Graal VM is just a marketing term that it's basically an umbrella project, and it has a bunch of things in it. It has Substrate VM, it has Truffle in it, and it has something in it that's called Graal compiler. I'm talking about the compiler, and just that. So we are not, at Twitter, we're not doing any polyglot or anything like this. OK, so why am I doing this talk? I want you to try Graal, the compiler. And there are a few reasons for this, why I want you to try it. There's the potential that you can save money by using Graal. As we do at Twitter, we save a lot of money. Then I want to fix bugs in Graal, so because we want random code, your code that you are running. We want Graal to run that code because we want the shitty code that runs in production to actually, that finds bugs. And then I would like to also improve Graal, the quality of Graal. If we throw more code at it, there are more code patterns that Graal has to compile, and so it will get more mature, basically. And when I give my presentations, then people come up to me afterwards and ask me, so is it safe to use? Or will it burn down my data center, right? Because this is an experimental compiler, so you never know. But I can tell you, Twitter is using it in production, and our data centers are fine. So they're still working. And you've used Twitter, and we're running some of our most important services 100% on Graal in production for about 10 months now. And I haven't lost any tweets, and I hope you guys did not, so it runs fine. Then people ask me, how do I use it? Very important question. And where do I get it? And the last 2 questions we're going to answer today. And then when they actually try Graal, they send me emails, and they're mostly complaining about benchmark numbers, right? Everyone has their own favorite benchmark that they're using for many years, and then they run this benchmark with Graal, and then what they tell me is usually, oh, Graal sucks, okay? And that's mainly because there are some properties that are very different to the existing compilers, and people don't know about this. And this is what this talk will explain, okay? So if you want to know more about the money-saving part, I have this other talk called Twitter's Quest for Holy Graal Runtime. There are a bunch of YouTube videos, so you just type that in on YouTube and watch it if you're interested. Good. So what is Graal? Everyone knows what a Java virtual machine is, I assume. HotSpot, yes. Who knows what a JIT compiler is? Oh, that's pretty good. That's The most hands I've seen ever. So for the ones who did not raise their hands, it's basically a JIT compiler takes Java bytecode. So you run your JVM, right? You run your application. It takes Java bytecode and then translates it, compiles it into native code so that your application code runs faster. And it does that during runtime, not like a C++ compiler ahead of time. It does it during runtime, and that's why it's called just-in-time compilation. Good. So Graal is actively developed by Oracle Labs. It has its official OpenJDK project. The source code is on GitHub, and it uses something called JVM JIT. We're going to talk about this later a little bit more, and it's written in Java. So Graal itself is written in Java. And if you're going to take away one thing from this talk, it should be that it's written in Java. And this is very important because the properties of a Java application are very different to the properties of a C++ application, right? And so let me see what the next slide is. I can't forget. Oh, yeah. Now let me talk about this. So you guys know what HotSpot is? The JVM of OpenJDK? Yes. Who knows what C1 and C2 are? Oh, yeah, OK. Some compiler engineers in here. I like that. You are my people. So C1, so HotSpot has two existing JIT compilers. One is called C1, or client compiler, and the other one is called C2, or server compiler. You might remember that -client, -server thing you sometimes put on the command line. So there are two compilers, and they are written in C++, right? So we are comparing ourselves, or Graal, we're comparing it to C2. So that's why this is very important. OK, first question, where do I get Graal? So there are two chips. One is called ahead-of-time compilation, which we introduced in Java 9. And so in Java 9, you can ahead-of-time compile Java class files or char files into a native shared library, right? And then the VM can pick up that code and run on it. So we introduced that in 9, but there's something even better. And it's chip 317, experimental Java-based JIT compiler. That's basically bringing Graal to the JDK, and that's in JDK 10. So if you're running JDK 10 or 9, then you have Graal automatically, basically. And so we're doing this today. We're using 10. So OK, first of all, I'm an Oracle Developers Champion. So Oracle gives me free cloud credits to use the Oracle Cloud and use it and do stuff with it, right? So I'm going to do a lot of demos today. And the way I do my talk, this one is very different to all the other talks that I've done before. And I think that other people do talks, because when you watch a talk where people do demos, at least when I watch it, I always wonder how many hours did they spend to make sure that the demo actually works, right? You set up your environment and blah, 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 make this work, patch here a little bit. So I don't do that. I do everything from scratch. So it's a little risky. A lot of things can go wrong. I'm going to go to this website right now, to the Oracle Cloud website. We'll start up an empty cloud instance, a container that has nothing installed, like literally zero. There's not even a Java installed. And then I show you all the steps that you need to do to run on Graal. That also means, as I said, a lot can go wrong. 2 conferences ago, the cloud container didn't come up, so that was a little unfortunate. And there will also be a couple of awkward pauses, because we have to wait for things to download. But it will give our translators time to catch up. So that's good. Let's go here. So we're going to this web page, and then we sign in. Here we go. You know, don't get discouraged. We'll get there soon. So we create an instance. We create a compute instance. And we cross our fingers that it works. Here we go. Okay. All right. So this is Tokyo. And we use this domain. I use Oracle Linux 7.4 because I haven't tried 7.5 yet, so I want to rule out one thing that can go wrong. Then we are choosing this one because it has 4 cores. And if you want to run your JVM, you need at least more than 1 core because you want your garbage collection to be in parallel and so on and so on. So we use that one. We use 4 cores. Then we need some SSH keys here so we can log in. So we add these, and that should be it. So blah, 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 create instance. So, okay, this is now provisioning. And we're waiting for this public IP address down here. Because we need this. And I hope it will come. Come on, Oracle. This is not good. This is really not good. Oh, here we go. Whew. Oh my God. That was close. Okay, so we grab that one. And then we log in. This doesn't work yet because this is still provisioning. I'm going to wait a little bit longer here because a week ago at GeekCon in Poland, I thought, oh, yeah, it will come up, right? And it never did. And then I switch over to the slides, tell you something else, and I didn't realize that it was not coming up. So we want to make sure that this orange thingy turns green and says running. That's what we're waiting for. Ooh, excellent. OK, very good. So now it will take another few minutes to actually start up, image it, start up, and so we can actually SSH in. So we're going back here. And in the meantime, I'm telling you about me. I like to talk about myself. So as I said, my name is Chris Thalinger. I'm working on JVMs for over 13 years now. And pretty much all the time, I was working on compilers. So I worked a little bit on the runtime. Never worked on GC. Have no idea how it works. I do compilers. And I like to call out people at this point in my talk because, so I like to call out old people. Who remembers GNU GlassPath? One old guy. It's him, right in the front. So back in the day, I was working on a different JVM, and that was before Sun open source Java. And so there was a thing called GNU GlassPath, which basically was a re-implementation of the core libraries. And we all met up at FOSDEM in Brussels. It's a conference, a free software conference. And we're drinking a lot of beer, right? And we thought we are the Wild West. We're liberating Java. Yeah. And then in 2007 or 8, Sun decided to open source Java, right? And so they also showed up at the conference. And we said, oh, yeah, you guys are actually cool. They bought us beer, so we liked them. And a few years later, I started working for Sun Microsystems. And I was always part of the HotSpot compiler team. So I was working mostly on C2, little bit C1, not so much. And then Oracle acquired Sun, and I stayed there for another few years and was working on different things. And these are, I think this is a short list of the most important things I've done. Number one is JSR 292, which is support for dynamic languages, so invoke dynamic, right? I was working on this. I wrote all of the compiler support for invoke dynamic. I did a little bit of interpreter support. Then John Rose and I, we realized that the first implementation we did not work that well, like performance-wise. And so we re-implemented everything, not everything, but most of it, and moved a lot of the logic that was in the VM before into Java, into the core library. So I wrote a lot of that code too, Java code. So if it doesn't work, you could technically blame me. But I don't think I made the bugs. I think people who actually worked on the code after me introduced the bugs. Then JAP 243 is the JVM CI that I was talking earlier about. It's the Java level JVM compiler interface. So it's basically an interface that Graal introduced or was using, and we just took this interface out of Graal and moved it into OpenJDK. And JAP 243 is in the JDK since JDK 9. So if you have a JDK 9 or later, you can plug in an external compiler that's written in Java, like Graal. And then I already talked a little bit about ahead of time compilation, so we did that in JDK 9 too. And ahead of time compilation, the way it's implemented, it's pretty much a command line tool that's written in Java. And this command line tool is just using Graal to compile code. That's all it's doing. So, and now work for Twitter. Greatest company on the planet. You guys agree, right? Okay, good. Okay, let's go back to the demo. And we hope that it works. I mean, it says running, but that doesn't mean anything. So I hope I can log in. Ah, good, thank you. All right, here we go. So we log in here, both terminals. And then, so as I told you, you guys can read that? Yeah. I told you there's nothing installed, right? We don't have Java, 0. We also don't have Git. So I'm going to install Git because we're going to need it later. And we are downloading a JDK 10. From the official website, we grab this file. And we download it, and we hope it's quick. Yeah, well, 30 seconds of waiting. I can't hear the translator speak anymore, so I think they caught up. That's good. I'm doing this pause just for them. OK, we have to wait for this. There's no other way around it. Oh, I could do a shadow dog in the meantime. OK, 4 seconds. Good. So we extract that guy, OpenJDK, and then we go in here. We set our Java home. Oops. So yeah, one other thing. Typing in front of a lot of people, So I might do a lot of typos, but I try not to. We're putting our Java on the path because we're going to use that quite a bit. There you go. And we do the same thing over here. Can people in the back read the stuff at the bottom? Yes or no? No. OK, good. So oh, come on. What are you doing to me? So we'd do it like this. How about now? Excellent. If you're in a country where you can't speak the language, this is like international. OK, here we go. So set this. Good. So now we have Java. Yeah, we do. And since, as you know, since JDK 9, we have modules, right? So there is a command line flag that's called list modules. And it's a list of all the modules that the JDK has. It's 75 modules. And we are looking for modules that are called jdk.internal.VM. Here we go. And as you can see, there are 3 of them. One is called jdk.internal.vm.ci. That's JVM CI. That's the Java API part of JVM CI. And then this other one, this guy, the jdk.internal.vm.compiler is Graal. It's just Graal source code packaged in a module. So if you have a JDK that has these 2 modules, then you're good. Remember? Thumbs up. OK. Let's go back to the slides. So how do you use Graal? You get a JDK with Graal. If you have that module, you're good. I should actually, instead of the check mark, I should use the thumbs up. It would be much better. And then you just turn it on. That's really all you have to do. Okay, so let me show you how to use it. We are going to run a bunch of benchmarks and demos, and I'm going to set an environment variable that's called Java tool options. And since JDK 9, G1 is the default collector, and G1, we're going to run a bunch of benchmarks, but G1 has a lot of heuristics built in, and we are going to look at GC log output. And G1 is just too complicated, so we are going to switch on parallel GC, because it's just easier to read and easier to predict. And we're going to use a pretty small heap. We're just using 512 megabytes. And we're going to set the start size the same size as the maximum size. And the reason for this is we are comparing C2 that is written in C++ to Graal and that is written in Java. And we want the heap expansion to be the same for both of the runs. Graal runs would expand the heap much earlier than C2 would, and then we would have GCs not at the same time. So this is not really comparing apples to apples. So if we set the start to the maximum, we're kind of leveling the playing field here. So we're taking this and put it over here, and we need some additional stuff here. So we're going to chap 243, and we scroll all to the bottom. And then it will tell you how to turn it on. So JVM CI is an experimental VM feature, so you have to turn that flag on. Then we do enable JVM CI, which just tells the VM, please enable the interface. Then you are allowed to use it. It doesn't automatically turn on the compiler. And then you have to tell it, use the JVM CI compiler. So this is all you have to do. Then you could tell it which compiler to use, but since today there's only one, that's Graal, we don't have to do that. So we grab these three, stick it in here, that's it. And then we can run java-version, and we can see, yeah, everything that we set is actually being picked up, and it prints out the version. Okay, very good. So there's a thing called print flags final, and we're going to look for all the JVM CI command line flags there are. There's like 10 or so, and you can see, okay, we've enabled JVM CI. We told it, oh yes, use it, and I'm looking for this one, JVM CI print properties. So we're going to run this guy, and it prints out a long list of all the JVM CI properties. I mean, it's long, okay. So there's a short section up here with all the JVM CI properties, like what, 5, 6, and the rest is all Graal. And they're actually Java properties, so -D, because Graal is written in Java, and we decided it's easier to pass options to Graal as Java properties than -XX command line. Okay, I'm looking for this one, JVM CI.init timer. And what it does, -D, because Java property equals true, what it does is it prints out logging when JVM CI initializes itself. Okay, so we should see some output here, but we don't. And so the question is, are we doing something wrong? And the answer is no. We're not doing anything wrong, but what happens is JVM CI is lazily initialized. And so no compilation is actually happening here or scheduled, so JVM CI is not initialized. Who knows? So we talked about C1 and C2, you remember that? Who knows what tiered compilation is? Okay, going to explain that. So tiered compilation is when you run HotSpot and you run your application, it starts out to interpret your code, right, which is really slow. And then it compiles your code with C1. And then it compiles the code in a way that it's collecting profiling data. And then after a while, you run that code. And then after a certain amount of iterations, basically, you recompile it again with C2. And C2 is using all that profiling data. So you go through tiers to actually end up with the fastest code you can get. And so this is tiered compilation, OK? And there are five-ish, four tier levels. 0 would be interpreted. It's not really a compilation level. So 1, 2, and 3 are different C1 compilation levels. And 4 is the top tier, which would be C2 or Graal. OK? So if we are running this, and we turn on print compilation here, and we can type it. Here we go. Then we see all the compilations that are happening for running dash version. It does not execute a lot of code, so it's not compiling a lot. And the third column, this one, is telling us which tier level it is. And as you can see, there is no tier 4. So the methods are not getting hot enough to actually schedule a tier 4 compilation, so JVM CI is not initialized. So what we have to do is we have to run a little bit more that methods are actually getting hot enough to be compiled on tier 4. So we download something called the Scala da capo benchmark. And it's here. So we grab this guy. Download that. Hope it's fast. Oh, yeah, that's quick. Okay. We can wait 10 seconds. Still 10. Yeah. These estimated time counters, they are never correct. Never. Good. OK, here we go. Here we have it. Now we're going to run this again with the init timer true and the Scala da capo benchmark here in the command line. So if I run this, right, oh, come on. If I run this with C2 over here, oops, yeah, then you can see -L just prints out all the benchmarks it has. It really doesn't do a lot. It just prints all the benchmarks it has. If I run this over here with Graal, you can see, oh, yeah, there's some output, right? We can see something. We can see there is a class initialized called HotSpot JVM runtime. It does some stuff, but it doesn't seem like it finishes, right? And that's correct. And the reason is the -L execution exits faster than the JVM CI initialization takes. So we exit the VM before it's actually done. So we have to run a little bit more. So what we're doing is we're running a small benchmark run of a benchmark called Aurora. And then you can see, oh, yeah, it's printing much more. OK, so we are same thing as earlier. And this time we're actually done with the HotSpot JVM runtime initialization. Took 78 milliseconds. Then there's something called a compiler configuration factory, which selects the compiler. But since we only have one, Graal doesn't really do much, so it just selects it. And then it initializes a class called HotSpot Graal runtime, does a bunch of things, creates the backend for our CPU architecture, and so on and so on. And then it runs the benchmark down here. We cannot see this one to finish because what the capo benchmark harness does, it redirects output into a file. And so when the benchmark starts to run, we can see the console output anymore. But that's OK. OK, so this run, let me redo this run again without the output. Takes about 5.3 seconds, something like this. And if we run that over here with Graal, it takes about 4.68. OK, so it's a very short running benchmark. 5 seconds is not very long. But Graal is about 500 to 600 milliseconds slower. And the reason for this is something we're going to talk about next. And it's called bootstrapping. Because Graal is just another Java application running in your JVM. It's really nothing else. So it loads Java classes. It has Java methods, right? And these Java methods at some point will be compiled to make the compiler faster because it's running, right? It's getting hot and it will compile itself, and that's what's called a bootstrap. It's a meta-circular problem because our JVM runs Java, but we ourselves are written in Java, right? It's a meta-circular issue. So it's called bootstrap, and we're going to do a bootstrap demo. I'll show you a little bit more about this. You can do, but please don't, you can do an explicit, oh God, bootstrap, here we go. You can do an explicit bootstrap with that flag, and then it does a bootstrap, and every dot is 100 method compilations. So this will take roughly 10 seconds. Yeah, here we go. So 10 seconds is a very long time to wait if you run something very short. For example, our benchmark that only takes 5. When you have to wait 10 seconds for the VM to come up or for the compiler to warm up, that's really not what we want, right? But that's not the case. That's not how it works. Because if you remember, if we run this guy again, it takes 5.8, 5.2, even better. So the difference is not 10 seconds, right? And the reason for this is, oh yeah, I deleted it already. But I don't know if you saw, when I did the bootstrap, it compiled about 2,500 methods, something like this. I run it again. So it's only a 600 milliseconds, 400 milliseconds difference. And the reason for this is that the compilations for Graal are happening in the background. We're not, the bootstrap JVM say, I said, don't use that flag. It's doing it all in the foreground and doing it until it's finished. And then it continues running the JVM or your application. But the standard way of running it is it just compiles it in the background. And you remember we instantiated that cloud instance with 4 cores. When we run this benchmark, or when you start up your application, most of the time you are not using all the cores you have, right? Startup of applications are usually in the beginning single-threaded, and then you fork a bunch of threads, and then you do things. But at that time, the VM can take all the cores that are not used right now and use it for compilation, right? So all these 10 seconds and even more are spread out across the cores you have. That's why we don't see it, or not really. If I run this thing, here we go. I run it 3 times, 3 iterations of that benchmark. Let's do that. Same here. We wait for it. It was 4.4. Should be roughly the same. It's a little fluctuating, but it's fine. Oh yeah, it's like 4.4, 4.5, something like that, right? So if we do the same thing over here with Graal, you remember the first one is slightly slower. So we have a 5.3, but this is already as fast as C2. So after 10 seconds, we've done, we are finished with all the compilations that we needed to do to get the compiler up and running and fast. And then we're already running at the same speed as C2. And this benchmark is very quick, right? It's only 5 seconds. Your application, your production application, whatever you have, does not start up in 5 seconds. It takes much longer than that, right? It has to compile more than, of course, yes, but Graal, the compiler itself, only has to compile it itself. So that startup difference you see will be spread out across your startup, so it's not noticeable. Good. Going back to the slides. So we learned that bootstrapping compiles a lot of methods, so like 2,500 with tiered. I'm not talking about non-tiered now. I don't have time. You can do it either up front. Don't do that. It's not a good idea. It was just for demoing purposes. Or it's happening on demand during runtime. That's what you want. And then one thing I left out was, by default, the way it's set up when you start your JVM, I was talking about tiered compilation. And when you use Graal, Graal itself is only compiled by C1. And the reason for this is C1 is a high throughput compiler, so it compiles methods quickly. And that's what we want. We want Graal to have native code as quickly as possible so that it can compile your application faster, okay? And then we also do this so that the compilations of Graal methods itself does not interfere or fight with the method compilations of your application. So that's what we do. So now is the time to talk about Java heap usage. Because as you remember, Graal is exactly. It's written in Java. So that means if Graal is doing work, all the memory it allocates will be allocated from the Java heap. Instead of, in the case of C++, C2 on the native C heap with malloc. It's different. Okay, so compiling application methods, and only application methods, because I just told you that Graal methods are compiled by C1, right? So only your application methods, or the benchmark methods in our case, will use Java heap memory. There's a flag where you can compile Graal with itself. I wouldn't turn it on or off. It's like the default setup is pretty good. And and Twitter, we are using this setup. We just let Graal be compiled by C1. We are still running on Java 8, by the way. You could, if you're running on Java 9 or later, 9, 10, you could AOT compile Graal, right? You could compile it ahead of time and then have native code for it, and all this bootstrapping problem would go away. If I had enough time, I could show you how to do it. It's not that complicated. But no one's really running on 9 or even 10. Even Twitter, we are still running on Java 8. Good. Let's do a Java heap demo then. So you're running this again. And we're turning on GC logging. And you remember we set parallel GC so it's easier to read. And Aurora, the benchmark, is a very compute-intense benchmark. As you can see, after the first iteration, so there are a few collections here, but they are forced collections by system.gc. The benchmark harness is just cleaning the heap before it starts an iteration, and it's cleaning it afterwards. So, and as you can see, we only allocated like 40 megabytes, 32 megabytes. That's nothing, okay? So it's a very compute-intense benchmark. It's just, crunching numbers. If we do the same over here with Graal, you can see, oh yeah, there's something happening, okay? And this is exactly Graal compiling the benchmark methods, right? So you can see we're allocating quite a bit, 132 megs, 137. There's still 100 on the heap after the benchmark run. And then our second iteration, we have one more collection. That's 135 megs. And then the last iteration, there's no GC happening anymore. And that's exactly what we've seen earlier with the runtime of the benchmark, because we're done compiling, right? So Graal has done its job, and it will run as fast as C2. So it's only the compilations at the very beginning of whatever you're starting. The benchmark, your application, you name it. All right. Let's go back here. So Graal uses Java heap memory. Yes, that's true. And I have to point out, today there's nothing like heap isolation. So the problem with that is everyone is tuning their heap sizes to exactly how much you need, right? We at Twitter do the same, because it's money. How many instances you can squeeze into a physical machine means how much you're paying. So, and then you give the instance, the heap, like a megabyte more because maybe you use a little bit more. That's how everyone does it. If Graal suddenly comes in and allocates 300 megabytes of memory, well, that's a problem, right? And then you will get an out-of-memory error. If you're really, really lucky, the out-of-memory error would be thrown into a compiler thread. And a compiler would just say, OK, I'm out of memory. Sorry, I catch this one, and I stop this compilation, and whatever. That's no problem. But most of the time, it will end up in your application. And your application is very likely not written to handle out-of-memory errors. So it is a theoretical issue. But we at Twitter never had that problem. And we're running 3 of our most important services, the tweet service, the social graph service, and the user service, they have thousands of instances, and all of them run on Graal. And we restart them multiple times a week for 10 months now, and we never had that problem. And the reason we never had that problem is because when you start up, when all the compilations are happening, your application is not fully up yet. It's not using all the heap. Because you start up, especially in a microsystem environment, you have to connect to other microservices first before you can actually accept production load. Then a lot of people, and we do that too with some of our services, you have a small warm-up, like you warm it up a little bit, right? At that time, everything is compiled. There will be a few compilations happening later, but they're usually not that bad. So most Graal memory usage is during startup, very important. And then remember, the memory is used anyway, either on the malloc heap, on the native heap, or on the Java heap. It doesn't matter. In a cloud world where you pay for how much memory your instance has, if your cloud instance has 4 gigabytes of memory, you cannot give the JVM 4 gigabytes. You all know that. Because there are other data structures that JVM uses, especially the compiler C2. It can allocate 200, 300 megabytes of memory sometimes. So in a Graal, when you run with Graal, you could technically give your JVM more memory because C2 is not compiling in the native memory. OK. I had, what, 10 minutes left? Good. So we're doing 2 things. I'm going to show you how to clone Graal from GitHub and how to compile it and how to run with the latest version of it. And we're doing that right now. OK. So I installed Git. I hope I did. Yes, I did. And so we're going to GitHub. And then we type in Graal. So everyone who's typing right now, are you doing what I'm doing? Yes or no? Yes or no? No? OK, anyway. So we're going to this one, Oracle Graal, and then we clone that URL here. So git clone. And I do a depth of 1 because the repo, it grew pretty big, and if I would clone everything, it would take too long. This is risky because it might be that the latest version right now does not compile. So, fingers crossed. We'll see. And then we need something called MX, which is a tool, a Python script, a huge Python script. Thousands. Oh, yeah, he's nodding. He's seen it. It's like 20,000 lines of Python script. Shit, I complained so many times about it. But Oracle Labs is using it for everything. You can compile Graal with it. You can run Graal with that. You can create your IDE configuration file. You can do everything with that script. It's very convenient, but it's way too big. So we put that on the path. Here we go. And then we go in here, Graal. And you can see there are a bunch of other things in here. I talked about Graal VM at the very beginning. So you can see Substrate VM is here. There's Truffle. But what we are interested in is just the compiler. So we go in here. And then we just type mx build. We set Java home. MX will pick up Java home. And we just do that. And then it starts compiling it. Ignore that output. That's not important. And then it starts compiling it. It downloads a bunch of dependencies it has. So it builds. And I said, I hope it builds. This build will fail. And the reason it will fail is it builds a small part for Truffle. And it's using libffi. And that's a C++ library, right, a C library. And so it needs GCC for that part. But as you remember, my cloud instance is completely empty. Do you really think I have GCC? No, of course not. So that will fail, but that's OK, because we only need the Java part. So we have to wait for this to finish. There should be a line that says archiving Graal. Yes, that's good. And then it's here, building JVM Java module. That's the one we want. Building Java module. Here we go. This guy. So as I said, failed, libffi, whatever. No one cares. So we go in here, and then there's a directory called modules. And this is the module we're looking for, so JDK internal VM compiler. It's a modular jar file. So we need MX here too, so let me put it on the path real quick. All right, and we go Graal compiler here, and then you can run with MX, you say mx-version. I'll probably go over a little bit. And then it will just use, okay, no, let me run this again with a -v. It will just run version, and here's the command line that it's using. So it's just picking up the Java we have, and then it's using this upgrade module path here. And as you can see, this is the modular jar file we just built, okay? You can run, let me do this. We run this benchmark again. We're only running once, that's what we need. And then we log class loading, and we grep for Graal VM. And then we have to do this, obviously. All right, here we go. And then, as you can see, the classes that are loaded here are being loaded from this JRT. And JRT is a JDK internal file system for loading files from modules. So it's just loading the classes from this module of the JDK, okay? If we are running the same command with mxvm, there we go, then you can see these classes are being loaded from the file we just built. So if you just run it like this with mx, or you use the upgrade module path, you just run on the latest version of Graal there is. That's really all you have to do. And then I like to do at this point, because I think it's fun, I like to run this benchmark with the latest version of Graal, and I always hope it's faster, but it never is. It probably takes, 5.6, even slower than before, so whatever. But so you can clone Graal from GitHub, load it into your IDE, play around with it, fix a bug if you want. There are a lot of compiler gurus in here. That's what I saw with a lot of hands going up. Just play around with it if you want. It's very easy to run. OK, so let me go back. So we did that. I'm skipping this production demo because we don't have enough time. But I want to show you the Scala demo that I have. And for this, we're going back here. And we are increasing our heap size a little bit to 2 gigabytes. And the reason for this is otherwise we would have too many collections, and then it would be hard to read or to see what I want to show you. So we're going to run factory. We're going to run 2 iterations of a benchmark called factory. It's the Scala benchmark. If we go back here and go to this benchmark page, and then there's a list of all the Scala benchmarks in here. There's factory. Here we go. The factory benchmark uses the factory toolkit for deployable probabilistic modeling to extract topics using latent I don't know. I don't know what it's doing. I really don't. But it's not important, right? So it's doing a lot of stuff. It's allocating a lot of memory, as you can see. It's allocating up to 750 megabytes, collecting down to 75 roughly. So it's doing a lot of GC work. And at the same time, it's doing whatever it's doing. OK. By the way, oh, yeah, here we go. That takes about 25 seconds to run that benchmark, OK? We run the same benchmark over here. And I think it was at GeekCon. I can't remember. So I was showing this benchmark, and I always say that I don't know what it's doing. And so after my talk, a guy comes to me and says, oh, yeah, this is very interesting. We're using LDA in production. And I said, what? What are you talking about, LDA? What? So it turns out this thing is LDA. I don't know what they're doing, but he said they are using it. So that's cool. Oh, I made a mistake, and no one corrected me. I forgot to increase the heap size over here. So here we go. 2 gigs, 2 gig, boom. Run it again. Okay. Doesn't take too long. Let me scroll down here. Make this a little bigger so we can see all of it. Here we go. And here as well. So as you can see, this is the GC ID, so the number of GC that we're doing. We started at 48 and we ended about 85. So that's roughly 40 GCs, 38 about. Over here, and it takes us 25 seconds to run that benchmark iteration. As you can see over here, it only takes us 17 seconds to run the same benchmark on Graal. And we start at 29, and we end at 48. So we're only doing 20 GC cycles. We're cutting the memory that's being allocated in half. This is ridiculous, right? This is, of course, because I'm giving a presentation and I'm doing a demo. This is the best benchmark you can find. Like, this is the best improvement I've ever seen in my life. And I want to look good, so I'm using that one, okay? You're not going to see that in production. If you're watching my other talk, the one I mentioned earlier, the Twitter's quest for Holy Grail runtime, I will explain, because the reason why Twitter is saving money is because of that. We're just not cutting it so much as here, but we're saving a lot. And because we're reducing CPU utilization, we don't need as many machines to do the same work. That's why we're saving a lot of money. And in the last minutes that I have, so the reason why this is happening is there are two very important compiler optimizations. The number one optimization is inlining. Right? Inlining is the mother of all optimizations. Inlining is very important. And the inlining implementation in Graal is better, different and better than in C2. And then there's an optimization called escape analysis. Escape analysis, I'm not going too much into detail, but it can eliminate object allocations. And C2 has the very standard escape analysis implementation. And Graal has something that's called partial escape analysis. And partial escape analysis can do more. It can eliminate more object allocations. And that, paired with the better inlining, gives us this. Also the same reason why we at Twitter see such a big improvement. All right, going back to the slides. So the summary of this talk is very simple. Just use it, really. Just grab a JDK that supports Graal, that has Graal, and turn it on. And I've done today everything, and everything went fine. That was good, good day. Everything you have to do, I showed you today. The slide doesn't have all the information, but there are recordings of this talk already on YouTube, so you can reproduce all the steps that I've done today. The reason why I chose to use a completely empty cloud container is because so you can see what you have to do. I did not cheat. I didn't cheat. So everything I did is what you have to do. And I would be really thrilled if you would give it a try. It would be nice if, I don't think you will use it in production tomorrow, but if you have a small, hobby project or whatever you want to run, try it. If it works, great. If it works better, even better. If it crashes, also good, because we want to find bugs, right? And it would be good if you find the bug and not we at Twitter, because then Twitter's down and no one likes that. All right, that's all. Tweet about this talk. Thank you very much.